Hello, I am Rami Muhammad. Today I will start my presentation for the high-rise selecting materials and loads applied on the high-rise and super high-rise buildings. First of all, the high-rise and super high-rise buildings have the key factors influencing the layout and material selection, like functional criteria, structure forces, economic and structural aspects. The beginning will be with the selecting high-rise and super high-rise buildings in the structural styles. So this paper examines the driving factors in the selection of materials, which can be used as a guide for potential construction design through a case study. The house buildings with more than 10 floors, including 10th floor, or more than 28 meters in height, as stipulated in China, can be classified as a high-rise building, as can the other type of high upright civil concrete structures above 24 meters. But the high-level buildings above 100 meter or 30 floor are globally stipulated as super high-level buildings. The building is regulated in Japan and France as super high buildings higher than 16 meter, but in America, buildings of over 152 meters or 500 feet are generally considered to be skyscraper, and buildings only super high-rise buildings can be designated in accordance with the new standards of the Council on Tall and Urban Habitat.
Now we will talk about the material selection of high-rise and super high-rise buildings. With the development of science and technology, the emergence of new structural materials brings new structural patterns, which brings huge influence to the structure selection of buildings. Along with the development of the steel and iron materials and compared with reinforced concrete, steel architecture materials have obvious advantages such as lightweight and high quality whose high strength to weight ratio is more than 5 times as reinforced concrete. If the gravity of the high-rise and super high-rise buildings is too high, it would bring impact on the design, construction, material, transportation, structure, earthquake resistance capability, and structural, technical, and economic indices of the buildings. Therefore, it's necessary to select the materials that can reduce the dead weight of the building, and meanwhile, the weight reduction could decrease the base load and the effect of earthquake, so as to reduce the cost of foundational and structural engineering. Therefore, rational building structural materials should be chosen, and the selection of the structural types should maximum the material performances. As a brief comparison between steel and concrete as a construction materials, the advantages of steel are lightweight, high quality, a high strength to weight ratio, can withstand earthquake more effectively. The disadvantages, fast in erection, fire failures, has 3 spots, loss of strength, good heat pipe, high expansion. The improvement we can do instead of using steel is to use composite steel concrete structures. The concrete advantages, very durable, can withstand high compression loads, higher fire resistance. The disadvantages, fire failure typically occurs in the form of spalling, can't withstand tension loads, less earthquake resistance. The improvement we can do to use fiber reinforcement or to use high strength concrete instead.
We'll talk about structural loads. Structural loads are forces or deformation or acceleration applied to a structure or its components. Type of loads. All types of loads can be considered as gravity loads and lateral loads. Gravity loads. Firstly, I will talk about dead loads. Dead loads that are relatively constant over time, also known as permanent or static loads. Secondly, live loads, dynamic or moving loads, temporary of short duration, consideration impact, momentum, vibration, dynamic of fluid. Environmental loads, these are loads that act as a result of weather and topography and other natural phenomena. These are seismic loads and snow, rain, and ice loads, and wind loads and thermal loads like temperature changes leading to thermal expansions and lateral pressure of soil and groundwater or bulk materials. And it's considered the most important seismic loads and wind loads. Lateral loads. Lateral loads first, seismic loads. Seismic loads building under Earth dynamics. Motion during earthquake building is subjected to inertial forces that act in opposite direction to the acceleration of earthquake excitation. This inertial force called seismic loads. And fault source make checking decrease with distance from fault and site checking, and will make waves amplified by soft soil make building response. Secondly, wind load. Load has the ability to during a building to sway, and wind velocity increase with the increase of height, and the variation of wind load with the variation of forms. Round shape make minimum wind pressure, and irregular shape make maximum wind pressure.
Hi, my name is Muhammad Abu Bakr and I'm going to talking about the structural system in the tall building. There are many types in the structural system for the tall building as we see, like rigid frame, shear wall, shear frame, flat slab, core, mega columns, outrigger frame, tube system, jagged frame tube, and finally the bundled tube. Rigid frame system economically don't have the sufficient resistance against terrestrial load in building over than 25 story because of large deformation. In this case, the total stiffness and so the economical height of the building can be increased by adding vertical shear truss or wall to the rigid frame to carry the external shear induced by lateral load. This interactive system is called shear frame system, which are composed of two main items, the shear truss frame system and the shear wall frame system. The shear frame system can be used up to 38 story. The jagged frame system, this system is more effective against lateral load than the framed tube system. In the jagged frame tube system, they are meet the axial compressive and tensile strengths of the diagonal braces. Trussed tube system can be described as the improvement of the frame tube system in order to increase the spacing between the column without inhibiting the tubular behavior. By connecting the perimeter column with exterior multi-story braces, the jagged framed tube system can be used up to 100 story. Mega column or mega core system is a second main advanced system which consists of larger cross section than normal, which is running continuously throughout the height of the building. In a mega core system, floor slabs are cantilevered from core shear wall like figure A, and also mega core system can be used with a strengthened cantilever slab where perimeter column are supported on like figure B. Mega core system can be used up to 57 story. In a mega column system, according to the function and appearance, it can also be named as mega frame system. Mega column system can be used up to 73 story. Outrigger frame system has been developed by adding outriggers to shear frame system with core so as to couple the core with the perimeter exterior column. Outriggers are at least 1 story deep, which consists of a horizontal shear truss or shear wall or deep beam at one or more levels throughout the height of the building so as to stiffen the structure. Outrigger system is used up to 163 story. Bundled tube system are a combination of more than one tube acting together as a single tube, like the framed tube or trussed tube. Among the advantage of the bundled tube system that their architecture structure has the ability to create tubes of different height in the system, and also the attainment of the higher building height and wider column spaces. Bundled tube system can be used up to 110 story.
Now we will talk about China Central Television system. China Central CCTV is a 234-meter tall building formed by a 9-story podium and two 50-story high leaning towers, which are linked at the top via a 13-story cantilevered. The brace tube structure gives the building the ability to withstand the likely seismic activity in the area. The challenges in the design were: China is an earthquake area. The temperature changes and the material deformation. Subsoil condition due to the presence of poor water and the probability of high settlement risks. Large free spans to meet the function of the building. For the loads on the building, we have wind load, seismic load, equipment load, and life load in the construction phase, and load to the sloping of the towers, which lead to a torsional and moment. Internal structure system can be divided to mainly two parts, internal and external. The internal part consists of two columns and core and outrigger. The columns and core slabs are supported by vertical steel columns and core. The internal steel columns and core are kept straight for functional layout and to house the lift and service the shaft. While the outrigger transfer trusses were used at a strategic location in the building to support floors in the overhang and for larger open internal spaces. For the external structure, an external continuous tube system was used by fully bracing all sides of facades to deal with the permanent and temporary load on the building and with the jagged structure in the building. The advantage of this combination led to less material required, more open and free internal spaces, better ability to redistribute the loads, simple construction technique. Now for the second case study, Burj Khalifa. Burj Khalifa case study. The architecture height was 828 meters, while the number of stories was 136. The structure system. It is an reinforced concrete building composed of hexagonal central core and outrigger. The hexagonal central core consists of reinforced concrete shear wall with thickness between 130 cm at the bottom to 50 cm at the top. This combination was developed to overcome the lateral loads. Wind force was dominant in the lateral loads. The maximum lateral drift at the top of the building were 1.2 meters. So a model F1 to 500 scale were tested using wind tunnels, led to the development of wings on the building, and at every stage the form of the building was reshaped after repeating these tests, which resulted in a reduction of the wind load to an absolute.
As a conclusion, this paper studies the structural system of the tall buildings and the factors affecting the construction and material selection and the risk problems facing the high-rise and super high-rise buildings, and also the way they are faced with them.